Hello grade 12s, welcome to this video on cell potential. In this video, I'm not going to be going through any examples. I will simply explain what cell potential is, what electrode potentials are, and what the standard hydrogen electrode is. That is what I'm going to do here, basically just theory. In summary, your cell potential is basically the EMF or potential difference of the cell that you create. So here we are dealing with galvanic cells. Galvanic cells have two half cells in separate containers connected with an external circuit or wire and a salt bridge. So an example of a galvanic cell, guys, any battery in your laptop, in your cell phone, cell or battery that you connect to a circuit with a globe, those are all galvanic cells, examples of galvanic cells. In a galvanic cell, we have chemical energy is converted into electrical energy. A chemical reaction takes place in order to provide us with electricity. So taking a look at this table of standard reduction potentials, you guys should have noticed that on the right hand side we have a whole lot of numbers. Those are called electrode potentials, and they are basically the EMF that you would find when you connect one of these half cells to your standard hydrogen electrode. So basically, your standard hydrogen electrode is your zero. That's your 0 point. You can actually see it over here. And everything else is measured against your standard hydrogen electrode. I'm going to explain that in a bit more detail later. All of this basically explains trends. If you see you have a high positive value, then you know that half cell will act as a good oxidizing agent. It will most likely be reduced. Substance will be reduced. If you go down, you're going to have a substance that will act as a good reducing agent and will therefore be oxidized. That is according to the trends over here. So what we say is a big positive number is a good oxidizing agent, and a big negative number is a good reducing agent. Those are the trends that they speak about here. Understand again, none of these reactions can take place on their own. We connect them to the hydrogen half cell in order to get the electrode potentials. That is very, very important. In order to get your cell potential, what we do is we take the electrode potential at the cathode and subtract the electrode potential at the anode. Remember, at the cathode we have red cat. So reduction takes place at the cathode, and at the anode we have an ox. So what's going to happen a lot of the time is you're going to be taking your values at the top and subtracting a negative value. Make sure that you don't mess up and just say minus a positive value if at your anode you have a negative electrode potential. A lot of learners skip this double negative and then get the wrong values. Okay, so we will go through more calculations, or we will actually go through calculations in the video to follow. Right now, I want to focus on the standard hydrogen electrode. Let's start off with the word standard. The word standard basically refers to standard conditions. You may remember in quantitative aspects of chemical change, we spoke about STP. Right? Standard temperature and pressure. Here we're sort of speaking about the same thing. Your standard temperature is still 25 degrees Celsius. Your standard pressure is still 1 atmosphere or 101.3 kilopascals. But we introduce standard concentration here. That will be the concentration of your electrolytes, and that is 1 atmosphere. So generally, whenever we are connecting some sort of galvanic cell, if you're required to, in your cell notation, include concentrations, it's going to be 1 mole per decimeter cubed, unless stated otherwise. If you have gases in any of your electrodes, then it's going to be at 1 atmosphere, 1 atm. Tm, and you indicate that in brackets in that cell notation next to your substance. Okay, so just take note of that, but the word standard tells us that we are dealing with a situation at standard conditions, standard temperature, pressure, and concentration. Now, notice over here that our standard hydrogen electrode looks a bit different. We have gas in this case, and we have a platinum electrode which is inactive. What basically happens here is in your standard hydrogen electrode, we have hydrogen gas at a pressure of 1 atmosphere that is bubbled. So we bubble it, right, over here, we bubble it into the cell over here. Okay, I don't know what's happening with my pen, sorry. We bubble it into the cell over there. Then what's going to happen is it will be bubbled over a platinum electrode. Now, platinum is an inactive metal. It will not take place in the reaction. It is just there to act as an electrode, to join my circuit in a sense. So we say that the hydrogen gas adsorbed onto the surface of the platinum. That is not a spelling mistake. We have the word absorb. A sponge absorbs water. The water goes into the sponge. Adsorb means to stick onto a surface. So if that is my platinum electrode, my gas bubbles literally go and stick onto the surface. That's what the word adsorbs means. And the reason why this platinum electrode is important is because if it was not there, my hydrogen gas bubbles would not adsorb onto the surface. They would bubble in and just bubble out. They just escape the substance. So when they adsorb onto the platinum electrode, they are able to interact with the ions that are in solution. They can actually make contact with those ions, and that is important in this case. And if we have any electrons that are entering the solution, same thing can happen over there. They say here that the platinum electrode is in contact with an electrolyte. The electrolyte is going to contain a diluted acid. The reason why we have diluted acid is, remember, if you have an acid like sulfuric acid, it's going to lead to a whole lot of H plus ions in solution, and that is what we want. I don't know why I wrote negative. Sorry guys, it's H plus ions. Yes, H plus ions, okay, in solution. So that's why we use a dilute acid, and that will be at 1 mole per decimeter cubed. Okay, so again, your hydrogen gas will enter and it will stick onto your platinum electrode. Based on what is happening, this over here may be oxidized, and then it will go and form hydrogen ions. Or if electrons are entering from the external circuit, then these will form gas bubbles, which will bubble off and out. Okay, so when you have a positive reading, so what's going to happen is, like over here, you might have a zinc electrode with zinc ions in solution and the zinc electrode itself. This entire thing is also referred to as an electrode. And you want to know what its electrode potential is. So you connect it to a hydrogen electrode. That is how we get all of those values in your table of standard reduction potentials, by connecting our one cell to our hydrogen half cell. That's what we do. Okay, when you do so, you're going to get a reading. If the reading is positive, like in the case on the right, here we have a positive reading. What it tells us is that the other electrode is positive and is the cathode. The hydrogen electrode is going to be negative and will behave as the anode, where an ox, in other words, oxidation, will take place. That means that our hydrogen bubbles are going to form hydrogen ions and electrons. Hydrogen is oxidized. Notice we have 0 volts as the electrode cell on our hydrogen half cell. If instead you find that we end up with a negative, like over there, a negative reading, then it indicates that that other electrode is behaving as the anode, and therefore our hydrogen electrode is the cathode. Remember, red cat. So that means that our hydrogen is being reduced. The hydrogen ions gain electrons to form hydrogen gas. This is all dependent on what the hydrogen half cell is connected to. Another way of seeing this, other than the positive or negative values, is if we have electrons exiting, moving away from the hydrogen half cell, then of course it means that oxidation must be taking place. Our hydrogen gas must be losing electrons. And if you see electrons are moving towards the hydrogen half cell, then it means that our ions must be gaining those electrons to form hydrogen gas. So that's another way of looking at it. What may be important, because they often make use of your hydrogen half cell in your exams, you may need to write down the shortened cell notation, but it's as you know it. We're going to have platinum. That's the main thing to not forget about. Your electrode is platinum, and then based on which cell it is acting as, somewhere you will have the hydrogen gas and somewhere else you will have the hydrogen ions. Okay, but that is basically your hydrogen half cell. That's what it's about. It's that none of these readings in your table could have been measured alone. We had to connect each of these half cells to the hydrogen half cell, which has an electrode potential of 0. We take it as 0, and these readings are measured based on that. Okay, that brings us to the end of this video. If you have any questions, you guys let me know. In the next video, I'll be going through examples involving calculations of your cell potential.